Okay, now we're going to have a line charge, and I'm going to go ahead and make that line charge orange. Okay, we have a line charge with lambda charge per unit length uniformly distributed over the line. We're going to draw a cylinder around this line charge. Okay, this cylinder is going to be not very close to the ends. No point on the cylinder is particularly close to the ends. So we basically make the whole cylinder far from the ends. Every point is much further from an end than it is from the line. Okay. Now, if that's the case, then by symmetry argument, we can make a couple of conclusions. One conclusion is that if we look at the thing end on and we look at the electric field has uniform magnitude all the way around the cylinder. Now, I don't think I said it, the axis of the cylinder is the central axis. The central axis of the cylinder is the line charge itself. So there's a symmetry argument that tells us that the field has to be identical and radial at every point, identical magnitude and radial, emanating out from the center of the circle that we see here, or emanating straight out from the line charge. Another symmetry argument tells us that the field is always perpendicular to the line charge, to the extent that we're far from the ends. Now, the symmetry argument goes something like this. If we have this line charge, and you look away for a minute, and I rotate this line 90 degrees or whatever, then this field has to rotate 90 degrees. If the field rotates 90 degrees, and one of these vectors is bigger than one of the others, then that larger field will then occur at an angle of 90 degrees from where it is. And that can't happen, because if I rotate this line 90 degrees, nothing has changed. It's still the same line, and you still have the same charge density. So that can't happen. The field has to have uniform magnitude all the way around. And similarly, if the field was at some kind of an angle at one point, if I was to reverse this line, then the field wouldn't be like this here, it would be like this here. And that would reverse the direction of the field, also reverse which end the anomaly occurs on. The only way we can have symmetry with respect to flipping the line 180 degrees is if all the vectors are perpendicular to the line. So by symmetry, the field is radial, of constant magnitude on the cylinder. And I don't think I made the statement that the field is perpendicular to the cylinder. Okay, well, the flux of an electric field or Venn field is could be expressed as E dot dA, where dA is a vector, but that incorporates the normal vector, but I'm going to write it more explicitly as E dot n dA, where n is a unit normal vector, a unit vector perpendicular to the surface. Now, a unit vector perpendicular to the surface of this cylinder is going to be parallel to the electric field, so that E dot n is just E, the magnitude of E. And we integrate E with respect to area. We're doing that here, and we're doing this over the surface of the sphere. This area integral goes over the surface of the, I said sphere, of the cylinder. Okay, over the surface of the cylinder, the electric field is constant in magnitude. This is just the magnitude now, so that comes out of the integral. And now we just have the integral of dA over the surface of the cylinder, which is E times the area of the cylinder. So very simple argument based on the idea of a flux. Gives us this result that the flux is E times A. Now there's another result And I'm quoting this simply from multivariable calculus. We'll probably take a closer look at exactly how this is connected to the multivariable calculus. But Gauss's law, basically the divergence theorem, says that the flux over any closed surface is 4 pi k q, where q is the charge enclosed by the surface. Okay, so this is what should be a familiar result from multivariable calculus, that the flux of any field any field that, I don't want to go into it, it's any field that can be calculated as the divergence of some potential function, but we don't want to get there. We're just going to take this as a given condition. I don't want to get into the multivariable calculus of it, just in interest of time, and since this is our first look at this sort of thing. So we have this, and we'll justify that a little bit more in a minute. But now, what's the charge enclosed by our cylinder? Our cylinder has length L. Didn't point that out before, it's labeled. Okay, if our cylinder has length L and radius R, I don't think I put the radius in. Let's write that down. Cylinder length L, radius R. Well, the charge is just the length times the charge per unit length, L lambda. And it follows from this, if you accept this, that the flux is 4 pi k L lambda. And from that, well, the field times the area is 4 pi k L lambda, which means that the field, magnitude of the field, is 4 pi k L lambda divided by A, which is the area of the part of the cylinder that's penetrated by this field. Now that doesn't include the ends of the cylinder because the field is parallel to the ends. E dot n would be 0 on the ends of the cylinder. Okay. The curved area of the cylinder is just circumference times length, which is 2 pi r circumference multiplied by length. So if A is 2 pi r L, we put that here, and we see that the 2 pi is going to divide into the 4 pi, leaving us 2. The L divides the L, that goes away, and we're left with just 2k lambda over R. So we've calculated the field of a long line charge or of a shorter line charge, as long as we're close enough to the charge that we're much, much closer to the line than to the ends.